Hello everyone, welcome to the next module of this course on physics-based animation. So far in this course you have seen how to do keyframe animation, and although it is an indispensable animation tool and widely used in practice in games as well as movie productions, it remains very tedious. So in this course, we will learn some alternatives animation methods to keyframes. One of them is performance capture, which is conceptually quite simple. We look at the performance of a real actor or object and record the animation, and then the key and the challenge is to retarget it to another character, to another situation, and so on and so forth as the game requests. Often this is done in real time in a game setting. Mature technologies for performance captures are motion capture or mocap, which is used quite widely these days, and an emergent technology which is also pretty mature right now is face performance capture, which we're going to discuss in quite some detail. In addition to these two big ones, there are some emerging technologies in performance capture, as you may have seen at SCA 2020, for example, the Zoo Builder. It's a tool meant to capture the motion of animals in the wild. This is pretty cool because actually the animals in the wild, there's no mocap for them because they're very difficult to put markers on and whatnot, and also difficult to do keyframing. So actually ways to capture them in the wild would be kind of breakthrough, and there are some work in this direction. Well, while performance capture is a very used technique in computer animation, and we will discuss it at length later in the course, an equally popular and mature technique is physics-based simulation or physics-based animation. If you look at this animation on this slide of the bouncing ball, we saw earlier how to do with keyframes. There was even, I think, a small video with me doing it in Maya in a very quick way. But it seems like for a bouncing ball, we should not need to do keyframes. If we can somehow follow the laws of physics, if we can just throw the ball and it bounces from the ground or in some walls, we should be able to simulate that and actually subsequently compute all the frames automatically using the laws of physics. And all we need is the initial frame, where the ball is located, where is the initial velocity, and then everything else should be computed automatically. Physics simulation, it is particularly useful also when a lot of objects are interacting with each other, and so the keyframes are practical. So if you see here, you have a lot of objects falling, and they do interact in a physical way. So, doing all this with keyframes, it would be very tedious to get right. And the physics simulation, once you have the tools in place, it's actually pretty straightforward. Another very common type of animation that is not practical to do with keyframes is cloth animation. As you can imagine, the cloth is made out of a lot of vertices, and it responds very well to the physics of the character. So a physics simulation is much more suitable rather than doing keyframe. The same goes for fluids. Fluid simulation is an example that would not be possible without physics simulation at all. You cannot possibly keyframe tens or hundreds of thousands or even million particles. And we can go even further. We can show hybrid simulations where we have, for example, massive fluid simulation interacting with rigid objects, right? So this is again, and on the left you have also the dam breaking. So this type of phenomena, they're completely infeasible without physics simulation. This is another cool example of a flooding. As you have seen in many video games and many movies, physics simulation for computer animation is a very established field. Some of the fundamental methods, for example, for cloth simulation are already 20, even some of them 30 years old. And as you know, they are used ubiquitously in games and movie productions as well. But this doesn't mean that physics-based simulation is finished, is over. It's still a very important research topic with a lot of open questions, as you might have seen if you attended ACA last week, or hopefully you will attend MIG next weekend. Here's a video that I took from one of the papers that does rigid body simulation. So there's always ways to improve, either make it the methods faster or make it more accurate or make it easy. Remember that everything here that we develop in this course are tools that are supposed to enhance, to be used by an animator to realize the animation vision. So really what all we do here is we present a number of tools that an animator can use. And again, your role here, this question, I received this question quite a few times. This role here is not to be the animator or to use these tools. Your job after you graduate from our program is hopefully to actually create new tools, which means, you know, a lot of maybe research and development at companies. So how does this physics simulation work? I'm going to start with a whiteboard, simple whiteboard example to get it started. Let's assume, to make things very simple, that we have only a one-dimensional object in one dimension. So we want to animate the motion of this point-sized object over time. So on one axis, we're going to have time. And on the other axis, we're going to have the position of the object. Let's call it x. And we have to have some sort of initial position. So let's say that at point t0, my point is located at x0. And the question is, how do I, if I want to move in time, at some time step in the future, t1, where is my point? Well, the truth is that without knowing anything else about the point, we cannot know. If I just look at t0, one snapshot, there's nothing I can do. I have no idea where the point goes. So I need more information. Let's say that I also have the velocity, the initial velocity here. Okay, so the velocity is a vector, so it can be up or down, right? So let's say that the velocity is up, and so it means that my point is going to move up by some amount. So it turns out if we have the velocity, we can roughly guess where this point is going to move in the next frame, probably somewhere up here. We can determine a bit more accurate where it should go by the magnitude of the velocity. But now at least I know it moves up. If the velocity is small, it moves a little up. If the velocity is large, it moves a lot up, and so on and so forth. So let's say we are now at this point here, x1. Well, now, next step is we want to figure out where the point is at t2. So how do we do that? Well, again, if we look only at t1, we have the position, but again, we would need something like the velocity. But if we assume the velocity is the same as before, this is kind of a boring example because it means that this object moves kind of with uniform speed, so it's not very interesting. So we need to figure out what is the new velocity here in t1. Well, how can we get that? Well, maybe we can add more information in t0. So what if we have the acceleration is 0, the acceleration of this particle? The acceleration is the rate of change of the velocity. If we know the rate of change of the velocity, then again we can estimate, we can know, okay, if the velocity was going up and then let's say the acceleration was positive, means that at t1 the velocity is going to be slightly bigger, right, because the acceleration was positive. So the velocity v1 here is going to be even bigger, okay? So if it's going to be even big or even bigger, it means that actually my x1 is going to be even further out. So, okay, I don't have too much space here. So let's say this is x2, so it goes up even faster. And so, okay, but then what do I do now if I want to do, let's say, t4 here? Well, I cannot keep adding initial conditions because anyway, the number of points I want to compute the position, they could be very large. But the interesting point is that the acceleration, I can actually estimate in every time step because the acceleration, it is related to the forces. So if I know which forces are applied on my object, as you know, I have the famous equation F equal mass times acceleration. So at every point of time, if I know the forces which are applied on my object, and I know the mass of the object, these are things that I assume I know, right? I know if I want to do an animation, I know what forces I have applied on my object. Then I can compute the acceleration in every step. And then if I compute the acceleration in every step, I can estimate the velocity in the next step and the position in the next step. This, what I presented you here is very schematic, and just to give you an intuition, we will look in depth how we formalize this in a very rigorous way. But this is the gist, right? I started with an x0 v0. From this x0 v0, I can figure out where the next position is because the velocity gives me roughly the direction in which the particle goes and how fast it's going, right? And then if I know the position in x1, because I know the acceleration in a0, because the acceleration is related to the forces, I can compute the acceleration in a0. And then acceleration tells me how the velocity is going to change at the next time step, right? So in this case, we say, okay, the velocity at the next time step, I should have drawn it in actually in green. The velocity at the next time step is bigger. And so using the velocity at time t1 and the position at time t1, I can again estimate where the position at times x2 is. Now I can compute the acceleration at time t1, we call it a1, also from the same equation. And then I repeat this process for as long as I need. I hope this gives you an intuition, and now we will see it in more detail in the next video.